Hello and welcome to this film about redox titrations. It's designed to follow on from the first film about redox calculations, and it basically takes the level of difficulty up just a little bit and deals with redox reactions that have taken place in titrations. We might have a look at what endpoints we might see during these experiments and maybe start to notice some patterns in some of the substances that are being used here. And once again, be a good idea if you've got your data sheet handy, but I will be putting up the half equations. Okay, so here's our first problem. A 0.1532 gram iron wire is dissolved in dilute sulfuric acid. You may well have done a very similar experiment in year 12. So this is quite a similar sort of calculation. The resulting solution containing Fe2 plus ions required 20.02 milliliters of a 0.0225 mole per litre potassium dichromate solution for complete reaction. Calculate the percentage of iron in the wire. Okay, let's do what we often do, which is to write a formula for the substance, for the thing that we're being asked to find. So the percentage of iron, well, that's going to be the mass of iron divided by the mass of the wire, 0.1532. Okay. Notice, again, we've got sulfuric acid here, and we had to use sulfuric acid to turn our iron into iron 2. Okay, if we hadn't done that, then we couldn't use this half equation here. All right, we'd have to be using some other half equation for perhaps iron being oxidized by dichromate. Okay, but we've deliberately turned all our iron into iron 2. Actually turn it into iron 2 sulfate by dissolving it in the sulfuric acid, but the sulfate is not going to react, it's just going to be the iron 2 ions. Okay, so here are our two half equations. We've seen these two before, so I'm not going to spend too long on this, but just notice that we've got 1 electron here and 6 there, so we'll multiply this half equation by 6 and we'll end up seeing that the number of moles of iron 2 is 6 times as great as the number of moles of dichromate. Okay, so what's the mass of iron? Well, the mass of iron, that's the number of moles of it multiplied by its molar mass, which is 55.85. Okay. What's the number of moles of iron? Well, the number of moles of iron, that's related to the number of moles of dichromate, as we've actually seen before. Okay. Number of moles of iron is 6, 1 mole of dichromate, so it's 6 times the number of moles of dichromate. What is the number of moles of dichromate? Well, the number of moles of dichromate is equal to its concentration times its volume, which is equal to 0.0225 multiplied by the volume, which is 0.02002. Okay, now let's plug some numbers into the calculator. Okay, I'll do this in a different color. For no particular reason, but I will. Okay, so that's 4.5 times 10 to the minus 4 moles. Multiply that by 6, and I get 2.70 times 10 to the minus 3 moles. Multiply that by 55.85, and I get 0.151 grams. And divide that by 0.1532, and I get 98.5%. Now, I did say at the start that we might just spend a little bit of time thinking about endpoints here, and also just spotting some substances that are coming up quite often. Here again, we've got iron 2 ions being oxidized. This is a very, very common thing to see, and here's a very common oxidizing agent, dichromate. Now, dichromate is actually orange, okay? And chromium 3 plus is green. Right, so as this reaction's happening, we're going to be adding an orange solution to this one, which will probably be very pale green. Okay, and as the dichromate is reduced by the iron, it will turn into chromium. Okay, so in other words, this orange liquid will fall in here and immediately turn green. When this stops happening, in other words, when we've used up all the iron, that orange to green colour change won't be able to happen anymore. so the dichromate will stay orange. The trouble with this titration is it's very, very hard to see when this has happened, because you've got so much green in there that you can't see that the orange isn't turning green anymore. All right, so just worth considering there. But basically, we ought to be able to think about what color changes are going to be happening in a titration and what our endpoint might be. Okay, but this does actually make dichromate a little bit awkward for use in titrations because it's hard to see its endpoint. Moving on to the next and final problem for this film, we've got a 2.82 gram sample of pyrolusite, or what on earth have I got this? Oh yes, right, okay. And so I was thinking, why have I got an iron 2 plus equation here when I've got manganese? But suddenly everything becomes clear. Okay, so 2.82 grams sample of pyrolusite ore was analysed for its manganese content by oxidizing the mineral to permanganate. So we're turning all the manganese into permanganate first, and then putting that into a 250 ml solution. A 20 ml aliquot of the latter, so the solution we've just made, was titrated with 44.81 milliliters of freshly prepared 0.212 mol per litre solution of iron 2 sulfate. Again, that's the source of iron 2 ions. Acidified with sulfuric acid, because notice, manganate is like dichromate. It needs acid to be able to act as an oxidizing agent. Determine the percentage of manganese in the pyrolusite. So again, percentage of Mn, that's equal to the mass of Mn divided by 2.82. The mass of Mn is going to be the number of moles of it times its molar mass, which is 54.94. We'll work this one out later once we've got the number of moles. The number of moles of manganese, well, that's the same as the number of moles. So the number of moles of manganese in this sample is the same as the number of moles of permanganate in our 250 mils. But the number of moles of permanganate in 250 is equal to, well, 12.5 times the amount that's in this aliquot. So 12.5 times the number of moles of manganate in 20 mils, because 250 mils is 12.5 times bigger than 20. Okay, so how do I find the number of moles of permanganate in 20 mils? Well, that's related to the iron 2 that it's reacting with. Okay, so the number of moles of permanganate in the 20 mils, that's related to the number of moles of iron 2. Is this statement correct? Well, I've got 1 electron here and 5 there, so I'm going to have 5 iron 2 ions. So the number of moles of manganate in 20 mils is actually 1/5 of the number of moles of iron 2. What's the number of moles of iron 2? Well, that's the concentration times the volume of the solution that contains it. Okay, so what's that? That equals 0.212, the concentration, multiplied by 0.04481. And if we start working our way back up now again, well, this number equals 9.50 times 10 to the minus 3 moles. So the number of moles of manganate is 1/5 of that. So if I divide that number by 5, so I get 1.90 times 10 to the minus 3 moles. I then have to multiply that number of moles by 12.5. And I do that, I get 0.0237 moles. And now I know the number of moles of manganate in 250 mils, and that's the same as the number of moles of manganese in there, because there's 1 manganese atom in a permanganate ion. So that number there is 0.0237 times 54.94, and that is 1.30 grams. And if I plug that into there and divide it by 2.82, I get a final percentage of 46.3%. Okay, so there is a couple of examples of redox calculations that come from titration data. As you can see, they're very, very similar to the problem that we did at the end of the last film. There will be another film that deals with some slightly trickier examples of redox titration calculations, but any questions from that one or any slip-ups that you notice? Because it's far from a rare thing for me to make a mistake in my calculations. If you point them out on the comments page, that would be really helpful. If you've got any questions that you'd like to ask, please feel free to come and get some help. And good luck with your practice, which I'm sure you're going to get plenty of.